we are using power series to evaluate limits. And we're also going to use power series to approximate some integrals also. So the rule of thumb in this section, anytime you see a function, you can replace it with its power series. So we're going to replace natural log of x with its power series here, and that will allow us to evaluate this limit in a different way. So obviously you could normally use L'Hopital's rule, but we just want to be creative, so we are going to use power series. All we do is take that ln x, replace it with its power series, and what we notice right away is that there is a common factor of x minus 1 that is going to cancel. So we'll divide the numerator by x minus 1, we'll divide the denominator by x minus 1, and this will give us the limit. Divide out all those x minus 1s, that's going to be a 1 minus x minus 1 over 2 plus x minus 1 squared over 3 minus etc. And as x goes to 1, what is happening with all these terms in the denominator? What goes on with all these terms as x goes to 1? Yeah, they all go to 0. So that tells us that our limit is 1. Wowie zowie.
For a second, I almost said infinity, and then I realized, oh, wait a second.
Yeah, don't do that. So that's it. Anytime we see a function, if we want to use power series, we can just replace the function with its power series and then carry on our merry way. So this one right here, we have the limit of x multiplied by that. So e to the 1 over x, that is going to be the exponential power series with x replaced with 1 over x. So this will be 1 plus 1 over x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed, etc. Yeah?
For the previous one, why did the first terms simplify to 0? If we're
Simplify to 0. This first term is, when we divide out the x minus 1, we're left with a 1. Right. X minus 1 goes into x minus 1 one time. So we're canceling one factor of x minus 1 each step of the way. You see it?
Wait, then where does x minus 1 talk?
Turns into a 1. If you divide x minus 1 by x minus 1, you get 1.
So we're dividing the top and bottom.
Yep. So that's the effect of that is that we're multiplying by 1. Right? If you divide everything in a fraction by the same quantity, the effect is that you're multiplying by 1. So if you can multiply everything by the same thing, or you can divide everything by the same thing, and the effect is that you've just multiplied by 1. So down here, this limit is as x goes to infinity. And all we have to do is combine here when we multiply by x. We're going to end up with let's see. So e to the 1 over x, we did that. Oh, I forgot part of this here. What part's missing? Subtracting the 1, thank you. Subtracting the 1. So we're subtracting the 1. Those 1s are going to cancel right here. Subtracting the 1, very important. So then we get the limit as x goes to infinity. When the x gets distributed, we will have this expression, 1 plus 1 over 2 factorial x plus 1 over 3 factorial times x squared plus etc. And where do all these terms go after the first term? Yeah, those are all going to go to 0. So it looks like every limit when you use a power series is equal to 1. Coincidence.
Can I just write a 1 on the test and then just give me the 5 points?
Just write a 1.
You'll give me the 5 points?
I'll give you 5 points
Alright.
out of
Use the
100.
voiceover as evidence then.
I'll give you 5 points out of 100. All right, let's do approximations. So here we have a binomial right there. So we have this binomial expansion that we've already found many times. Maybe I should say several times. And so same idea as the last slide. We're just going to replace this function with its power series. So if we want the power series here, it's going to be looking like this.
How many terms will you always want us to do?
It'll say in the problem, so usually it's 4 non-zero terms. That's kind of typical. All right, so there we got it. Any questions there? So we just replace the x with x to the 4th. Now let's just double check our interval of convergence. If we replace the x over there with x to the 4, we also have to replace it here. And then you can either do that sneaky algebra that I've sort of shown you here. You could just take away that thing over there because it adds no extra solutions. And then if you take the 4th root of both sides, so if you do the 4th root of x to the 4th less than or equal to the 4th root of 1, obviously the 4th root of 1 is 1. And the 4th root here is absolute value of x. All right, the square root of x squared is absolute value of x. The 4th root of x to the 4th is absolute value of x. 6th root of x to the 6th, absolute value of x. Okay, so then this gives us our interval of convergence not actually changing. So that's an algebra way to do it. You can also do the little graph technique that I showed you as well. It does not matter. So there's our interval of convergence. These numbers are within the interval of convergence, so we're okay. Well, this is a power series. All we have to do is integrate term by term. So when we integrate term by term, we end up with this. Whatever 13 times 16 happens to be. And this is going to go from 0 to 0.2. Plugging in 0 doesn't do anything. So then we're going to have 0.2 plus 0.2 to the 5th divided by 10 minus 0.2 to the 9th divided by 72 plus 0.2 to the 13 divided by, that's 13 times 16. Someone type that out real quick, 13 times 16?
Hypothetically, what would happen if they gave us a range that wasn't entirely in the...
Then we just couldn't use this technique. Yeah, we can't do it if it's, the only way you can use it, the only way a
It's
power...
208, 13 times 16.
How much?
208, 13 times 16.
208. Yeah, we can only use a power series. Power series is only going to work if we happen to be in the right range. Otherwise, we couldn't use it. Okay, so now notice that other than that 0.2, aren't we dealing with an alternating series? So we could think of this as an alternating series with 0.2 added to it. So we're going to just use our alternating series stuff that we've done in the past and just look at the magnitude of the terms. And so all we have to do is figure out, so this one said we want to know when it's less than 10 to the negative 5. Originally it was 10 to the negative 4, but that was not that interesting. So let's try 0.2 raised to the 9th power. Is that value less than what was it, 10 to the negative 5?
Yeah.
So is it less? Right, that's definitely less. So let's check the term before it just to make sure. 0.2 raised to the 5th power. Oh, and I didn't divide by 72. No,
But that's just going to make it even smaller.
that's not going to change anything if it already meets the criterion. Divide that by 10. So this one, is that less? No, that's not less because there's 5th decimal place is a 3, 5th decimal place is a 1. So the term that's less is that 9th power term. So this term right here has magnitude less than what we are interested in. So this term right here, that's less than 10 to the negative 5. So that means we're going to add up everything that's in front of it. We're going to add these up. So if it asks for the approximation to be less, then we just type that into our calculator and get whatever that number is. So that'll give us, after we type it in to our calculator.
So only the first two?
Yep, in this case, only the first two.
The decimal approximation?
Yep, it'll be a decimal approximation, yeah. You know, when you add these two together, we'll get a decimal approximation. And that'll be within 10 to the negative 5 of the actual sum.
Do you really have to use power series for that one when you know that the integral of inverse tangent is 1 over 1 plus x squared?
That is not the antiderivative of arctangent.
So that's the
I'm so
derivative.
disappointed in you.
I went the wrong way.
You went the wrong way. Yeah. If you could integrate it super easily, but we do know how to integrate it using what technique that we do last exam? We integrated arctan with louder? Trig sub, yeah. Trig sub is how we integrated all the inverse trig functions. We could use trig sub. Alright, so this is going to be the integral from 0 to 0.35. So once again, we just replace the function with its power series. Usually we go to 4 non-zero terms. It's a polynomial, so we can integrate term by term. So the antiderivative here is going to look like this. And that's from 0 to 0.35. Once again, we have an alternating series. Plugging in 0 doesn't give anything. So we're just trying to figure out this alternating series. So once again, we are seeing that we're doing lots of error approximation with the alternating series. And when you get into a higher class, you'll do this more generically. So we just need the first term that's less than 10 to the minus 5. No big deal. And then we add up everything in front of it. So let's see. What term? I'm going to guess 0.35 to the 6. Divided by 30. Is that less? So we have 5th position, 1, 2, 3, 4, 5th. Nope, not yet. So this one is going to beat it by a lot, I would suspect. So 1, 2, 3, 4, 5. Yep, so that one's less. So we just add up everything in front of that position. So you would just type the stuff in front of it into your calculator and get that approximation. So this is first less than 10 to the negative 5. So you're going to put these all into your calculator, add these up. And that's the approximation. Any questions on any of those steps? All right, well, let's go to this last page. The only thing here, it's more of an observation than anything. If you have the power series for a particular function, you can find infinite series representations of numerical values. So the square root of e, that has an x value of 1/2, so this is an infinite series representation of root e. Let's put that in the denominator, so 1 over 2 factorial times 4. Here, same thing, put it in the half, so we're going to get 1/8. So an 8 in the denominator, plus etc. So that's an infinite series representation of square root of e. And you can get numerical values for all these. This is a pretty easy one to simplify. So we'd have 1 plus 1/2 plus 1/8 plus a 48th plus etc. So that is just an observation more than anything. We're not going to do anything else with it. Caitlin?
So you just plug in whatever number it is for x, just like what we were doing before, but now it has like a numerical value.
Right, so square root of e is e to the 1/2 power, so if we replace that x with the 1/2, we're getting an expression for that number. So down here, sine of 1 radian, if that's the power series for sine, sine of 1 is found by simply plugging in 1 for x. And this is now an infinite series, not a power series. Power series has an x in it. So this is an infinite series for sine of 1 radian. And then we were done with chapter 11. We done? Now we get to review. Let's go all the way back to chapter 10. 10 point whatever. So let's go to a review for our test on Thursday. So all the topics, no note cards, no phone calculators. You can bring a graphing calculator that does not have an integral button, no integral button. So there are all the topics. So let's go ahead and start doing some of these. This first one, I'm not going to ask you a word problem on this test, so we can pass on that for now. Let's go to log limit. So log limit, if you're asked to use the log limit process, you have to use the log limit process. You can't use the shortcut. So let's do one of these with the log limit process. And then we can do the other one with the, well, let's do this one with the shortcut. What does this go to as n goes to infinity?
E to the 3/2.
6.
E to the 6? So we multiply those coefficients. We multiply this right there and that right there. So multiply them. But this one we're going to do longhand. So we do this longhand. You don't have to, but usually we like to replace the n's with an x. You don't have to. So we've got that as our function. And then we take the natural log of both sides. So the natural log of y will equal 4x times the natural log of x over x minus 3. And then we take the limit of both sides. And on the left-hand side, that limit can move to the inside of the log because the log is a continuous function. And then on the right-hand side, we want to rewrite it so that we can apply L'Hopital's rule. And so we typically are going to do this by moving something into the denominator. So in this case, we'll just move that whole 4x down there. That's the easiest way. Now it satisfies L'Hopital's assumption. We get a 0 over 0 indeterminate form, so we can apply L'Hopital's rule. So this is 0 over 0. We're going to apply L'Hopital. L'Hopital says take the derivative of the top and the bottom. What is the derivative of the denominator?
Negative 1 over 16x squared.
The derivative of the denominator, that 1/4, you should be thinking of this as 1/4 x to the negative 1.
Would it be easier to clean up like what's in the log before we separate it? Because now we have to do a division.
Simplify what's in here?
Yeah,
You can't simplify anything in there, though.
but you could if at the start you flipped it with the negative x component.
Oh, you could do that. But if it says use the log limit process, that's not going to help much. You've got to do logs and limits anyway.
Should be
It won't change much.
should be 1 over negative 4x squared, right?
So this is 1/4 x to the negative 1. So it's negative x to the negative 2. So it's negative 1/4 x to the negative 2, which if we write it as a fraction will be negative 1 over 4x squared. That is a very common place to make a mistake. That 4 is a coefficient. Okay, you don't need the quotient rule or anything. So now we take the derivative of the top. It's 1 over the inside. So 1 over the inside is going to be x minus 3 over x. And then we have to differentiate the inside. So that's low d high. D high is 1. So low d high is just low. Low d high minus high d low is also 1. All divided by low squared. So we cancel out these x's. And let's see what we have ended up with. So we are going to have limit. We're going to write everything as fractions. So x minus 3 over x. And then let's see what's left in that top right corner. To me, it looks like a negative 3 divided by x minus 3 quantity squared. And then we're dividing by a fraction, which means multiply by its reciprocal. So I'm just going to write it like that. And then we're going to do some canceling. 1x minus 3 cancels. So in the denominator, we have x minus 3. In the numerator, 1x cancels, so we're going to end up with 12 times x. And this limit as x goes to infinity is equal to, well, here at 12. Confirmation, 12, something else?
I agree.
I agree with 12 too. Okay, so 12. So you have 3 ways to do that limit. You could use L'Hopital again. You could divide by the highest power of x. You could take the dominant term in each numerator and denominator. Doesn't matter. So now our last step is to exponentiate both sides. So the limit of y as x goes to infinity is e to the 12. So that is what we were trying to get to.
So when it comes time for exam, we should just do this anyways, because more than likely it'll ask us to use a lot.
Yes.
Okay.
Yeah. Now, if it comes up in another problem, like an endpoint where you're finding an interval of convergence, it's totally fine to go with shortcut. So if we were going to do this shortcut, we would do what Ari suggested originally, which was flip this. And if we flip this, then we make the exponent negative. And then we can separate this into 1 minus 3 over n to the negative 4n. And then that limit, as n goes to infinity, is e to the coefficient of the exponent multiplied by that, right there. So that's e to the 12. So that's how you can check your work super easily. Caitlin?
Is it okay if we like configure the problem differently?
What does that mean?
Well, if like, let's say for like the 4 at the top, we would just keep it as a multiplier instead of,
This, oh yes, 100%. Yeah, if you want to just leave this 4 out here as a multiplier and only pull the x into the bottom, that's totally fine. A lot of people get confused by separating these and they want to think of it as one thing, but you can definitely separate it. Yeah. All right.
Sort of a general question I had. How does a natural log bring the 4x down?
It's from the log properties. We have a log property that says log of a to the b is b log a. So we're just using that property that exponents become coefficients. So that's why we take the log. Most of the time in calculus, you take the log in order to pull an exponent down. Yeah, that's kind of... Let's take a look at limit. All right, minus 0.2 to the n as n goes to infinity. What's that equal? Limit minus 0.2 to the n. Hello?
0.
0. Everyone agree? All right, take a number that has a magnitude that's less than 1. As you do repeated multiplication, it gets tinier and tinier. And then this is the other basic limit. If you take the limit as n goes to infinity of a base that's bigger than 1, that's going to be infinite. So just two basic limits. Make sure those make sense. Let's go to, we'll come back to some of this other stuff. Let's go to geometric series. Let's hit the things that are most important first. So geometric series, here some are. Tell me, so for a geometric series, we have an R, which is, normally when we write it in the arc form for a geometric series, we're thinking of it as A, R to the K, and frequently K starts at 0, it does not have to. And so we need to identify A and R if we're going to find the sum of these series. Now, there's a few ways to get at this, but regardless, you need to at least show that this is going to be written in standard form as 1/9 raised to the k. K starts at 0. So we're going to use the exponent, the part of the exponent that's right there, 3 to the negative 2, that's a 9th. So that's how we would write it in standard form. And then tell me what A is equal to.
1/10.
And tell me what R is equal to. So this is how I know you know it's geometric. You have to show some work here. You have to write it down. And then S is going to be A over 1 minus R. And before we do that, though, you also must notice that this is less than 1. Therefore, we know it converges. It doesn't matter if it converges or diverges. You still could plug in those two numbers here. I saw a couple of you do that on the worksheet. You can't plug it in and have a number that makes sense unless you have convergence. You could plug those numbers in and get an S value, though, but that's not what you should be doing. First, you have to get convergence. Once you have convergence, then you can say, oh, okay, this is this is what this is going to be equal to. That makes sense?
Do we have to say when r is less than 1, it converges, or is it enough to say r is less than 1?
It's enough to do this. This tells me that when r is less than 1, it converges. Yeah, so if you just write that, that's totally fine. So notice, though, that even if this r value is 3, you could plug in a equals 1 and r equals 3 and get a number. You get a negative number. But that number is meaningless. So you only find that s if your r value is under 1 in magnitude. It's the only time it makes sense. All right, how about this one? So same idea here. We need to rewrite this so that it's in standard form. So same type of thing. We're going to take that -2 and apply it. So we're going to flip it. And what are we going to get when we do this? 16 to the k?
Which is bigger than 1.
So what is the a value?
0. Sorry, 1.
What is the r value?
6.
So here's where we would say this is greater than 1, therefore it diverges. So then we don't go further. You don't go find s. Even though you could plug in 1 and 16 and get -1/15. That number's meaningless. How about this one? This one requires a little more finagling. So to get it in standard form, to get it in the arc form, we need to break some things apart here. So how can we break this numerator apart? Like, we want to have it in this arc form. We want just a k in the exponent position, not k plus 2, k minus 3, k. We don't want any of that. So how are we going to simplify this numerator?
Multiplication. Or
So-
break apart.
So tell me what to write.
-2 to the k, and then -2 to the -3.
Close. This negative is not included in the power,
Oh, okay.
because that negative is not wrapped up in parentheses. So that negative is floating out in front. It's not affected by the exponent. So the k minus 3 only touches the 2, so the distribution is going to be 2 to the k and 2 to the -3. Denominator, 3 to the k and 3. All right, so we're getting close. So let's see. We're going to put the k's together, so it's going to be 2/3 to the k. All right, so we've got rid of the two factors that have k. And what's the number that's going to sit in front there? What's the a going to be?
1/24.
1/24. And then the sign, so this right here, that is going to be 1/8 down there, so that's 24, and then the minus sign, yes. And we can put the minus in several places. I'm going to put it in this numerator right there. Okay, so now we need to identify. So a is -1/24. And r is 2/3. Now we have to do something like this. This is less than 1, therefore converge. Now we can use the S formula. So we only use the S formula if we know we have convergence. So S will be A divided by 1 minus R. I'm going to multiply everything through by 24. Multiply by 24, 3 goes into 24 8 times. So we end up with -1/8. Minus an eighth.
Almost minus a 12, but not quite.
Not quite. So geometric series, super important. Telescoping. So these are our first two series that we were able to find S for. Geometric and telescoping, those are the two that we can find the actual series sum. Most we can't. Okay, so this guy. Stretch you. Does not want me to stretch you. Okay. Zoom in a little. Telescoping usually involves some sort of factoring, some sort of PFD possibly. So we have to first take this and rewrite the summand. And when we rewrite the summand here, we're going to factor the denominator into k plus 3 and k plus 1. So there is our factored summand. And we use PFD. We're going to break it apart into a over k plus 3 plus b over k plus 1. Okay. Multiply through by the left denominator. So we get 2 equals a times k plus 1 plus b times k plus 3. Both of those denominator factors are linear, so we can use our method of convenient values. What are the two convenient values that we're going to use?
-1, -2.
Yep. So plugging in -1 first, the equation that we get from our PFD equation here, if we plug in -1, that goes away. -1 plus 3 is 2. So we get 2b. 2b. So b is 1. Then let's plug in the -3. On the left we have 2. And then we get -2a plus 0 on the right. So this tells us that a is -1. Alright. So now we have the series rewritten in telescoping form. So 0 to infinity. A is -1, B is +1. So let's rearrange it. I'm going to write it this way just so that it's plus and then minus. It's a little easier to visualize it, I think. So we're going to have that minus this. And it's all inside the summation. They don't usually do it, but technically it feels like you should have parentheses around that so that everything's wrapped up inside. But shortcuts. Shortcuts. Okay. So what we did with the telescoping series is that we need to find S sub n. We find S sub n, and then we can take the limit of S sub n. So S sub n is the sum of the first n terms. So S sub n is the sum of the first n terms. So we're going to start out with k equals 0. K equals 0 is going to give us 1 minus a third. So that's k equals 0. So I'm going to put the k value down here. So k, there was k equals 0. Now we're going to go to k equals 1. So we plug in 1 up here, we get a half minus a fourth. So this is when k is 1. So we're going to go to k equals 2. When k is 2, we get a third minus a fifth. And usually that's far enough to see the pattern. Maybe I'll go one more just to be darn sure. So I'm going to plug in a k equals 3. We get a fourth minus a sixth. So this is k equals 3. And now we can see our pattern really well as we're going from left to right. The second part, we skip a term, and then we wipe out the first part of the next after a jump. So this second right here is going to cancel with the first part of the next after a jump. So those are going to go away. So going left to right, second parts are vanishing. So this second part's going to vanish with something over here. This second part's going to vanish with something over there. The only parts that remain uncanceled will be these two first parts. So those are going to stick around. Now, we need to go all the way out to the nth term. Not the n minus first term, not the n plus first term, the nth term. What is the k value for the nth term? No. N minus 1. Right? Because we want n terms. So if we start counting at 0, if we want n terms, the last k value would be n minus 1. And what would the k value of the term prior to that be? N minus 2. Go 1 to the left. So we subtract 1. All right, so let's plug these k values in to that. So we plug in n minus 2 right there. So n minus 2 plus 1 is an n minus 1 in that denominator. Plug in n minus 2 here. So we get an n plus 1. And then the nth term is found by plugging in k equals n minus 1. So it's going to be 1 over n. And then over there, 1 over n plus 2. So that is S sub n, the sum of the first n terms. And when we go to cancel, we didn't write the third one here. Like putting a third one would make it a little clearer, but we should be able to discern the pattern. So look at the 4 terms that we wrote here, and let's start with the 4th term, and let's move right to the left. So if we're moving right to left, it's the first part that cancels with something in front of it after a skip. It's the first part that cancels with something after a skip. So in other words, going this direction, first parts are going to cancel after a skip. So it's going to look sort of like that. So these first parts are going to cancel, and the only things that will not cancel are these second parts. So these second parts are both alive and well. So that means that we finally can write down the closed form for S sub n. S sub n is going to be 1 plus a half minus 1 over n plus 1 minus 1 over n plus 2. So that is S sub n. You can add the 1 and a half for sure. You don't have to, though. It's fine if you don't, because we're more interested in taking the limit. So the limit of S sub n as n goes to infinity is going to be what?
3 halves.
3 halves. So there is the sum of the series. So we get a closed form for S sub n, and then we take its limit to get the sum of the series.
And that's about as complicated of a telescoping series that you put on there.
Mm-hmm. Yeah.
And you wouldn't put one on there where you don't have to do PFD?
You should be able to do PFD, yes. Be able to do PFD.
Didn't you also say that a series where you can find S of n are also the only series in which we can tell which way diverges?
Say that once again. Series that we can find S of n.
Are the only series that we can find in which way it diverges?
There are some of the other series, if we can find S sub n, it's really obvious how it diverges. Some of the other series we can figure it out, like an alternating series, you can sometimes tell that it's alternating and it's going to diverge by oscillation, or it's going to diverge because of oscillations that get large or even just small oscillations. So some series you can tell that aren't these. But for sure with these you can. You can tell how it diverges if it diverges. Correct. How it diverges. Ooh, dt. So the divergence test, remember this is our first test of the 10. We're going way back now. Way back to the day after exam 2. So the divergence test, we take the limit of a sub k, and if that limit is not 0, we know the series diverges. If the limit is not 0, it must diverge. And if the limit is 0,
It does not converge, and we don't know if it diverges or not.
so if the limit is 0, it's inconclusive because it may or may not converge still. So we need more information. Okay, so bottom line, take the limit as k goes to infinity. So we're taking the limit as k goes to infinity. Indeterminate form, infinity over infinity. So if we get indeterminate form, L'Hopital. So we're going to use L'Hopital's rule. This is infinity over infinity. So L'Hopital applies. So we take the derivative of top and bottom. So this is 1. Let's write this as 1 over 2 root k. So k to the half, it's 1/2 k to the minus 1/2. And then down below, what is the derivative of ln of 2k?
Sorry, what?
1 over k. 1 over 2k times 2. 1 over the inside times the derivative of the inside. So 1 over 2k times 2. So if you wanted to write out all the steps, you would have that. And then the 2's would cancel. Okay, let's see where we're at. So this is going to be 1 over 2 root k from the top, and then let's flip the bottom. K over 1, so we have that.
So k over 2 root k.
K over 2 root k, and now root k goes into a k. Root k times. So we have that. Right, k is root k times root k. One of the root k's cancel.
So that's.
Or it's k to the 1 divided by k to the half. It's k to the 1 minus 1/2. So you could use laws of exponents. You can use several different things. So what is our limit then? Infinity. So our conclusion, this is not equal to 0, therefore diverge. So if that limit is not 0, it must diverge. So that is the divergence test. Another one here, we're going to take the limit as k goes to infinity. And so we have root k over k cubed plus 1. The simplest way to deal with a fraction that's got one part square rooted, usually the simplest way is to push the limit inside and to turn the denominator into the square root of a square.
Couldn't we just do, say that infinity to the third grows faster?
No. That's not, it's true, but that doesn't prove it. So you just saying k cubed goes faster than that's not enough. We need to do some sort of math. Just a little bit of math. A wee bit of math. So now in here, we have a property that says, okay, now we're taking the limit of a quotient of polynomials so we can look at the highest power of each polynomial. So in the bottom, what's the highest power of k? K to the 6. Yeah. So we could do this. So we can do that. So that's choosing the highest power in the numerator, the highest power in the denominator. That's totally fine. And so now we get to a place where we can legitimately solve it by inspection. That limit is 0. So what is our conclusion?
Inconclusive.
Inconclusive.
We don't have a conclusion.
Our conclusion is there's no conclusion.
We have agreed to disagree.
I agree. I agree.
Or if we just,
What was that, Anna?
can we just like ignore the one because it doesn't do enough?
So if we were going to use like a comparison test, we could do that. Like at this stage right here, we don't have a polynomial over a polynomial. So we don't have that same luxury. Once we get polynomial over polynomial, then we can ignore the less significant terms. But at this stage, that's not a polynomial. So we can't quite go that way yet. So we could ditch the one if we were going to go for a comparison test, but that's not what we're going to do here. All right. We're getting to, ratio test. I need to increase the font on this slide. These slides. Okay. If we are going to use the ratio test, we need to have a sub k. Because the ratio test is a sub k plus 1 divided by a sub k. So this is not written in closed form right now. No summation notation has been given. But we can find it really easily, I think. So the denominators, let's look at the pattern in the denominator. Isn't there repeated multiplication by 6? And I assume that that's multiplication by 6 also. So times by 6. 1200, 1260, 1296. Yes, totally agree. How about the numerator?
Looks like k to the 5.
Say that again. It looks like k to the what?
5.
K to the... okay, so this would be 2 to the 5. Is that what you're saying?
Yes.
And this is 1 to the 5. And this is 3 to the 5. And this is 4 to the 5. Let's check. So 3 to the 5, that's 9 times 9, which is 81. 81 times 3 is 243. 1024, so that's 4 to the 5, so that's 256 times 4, which is 1024. Yeah, good. I agree with you, 100%.
K equals 1 on the bottom.
So k equals 1. That's where you're saying it starts at? We'll double check. So that's going to be k to the 5th divided by 6 to the k. Everybody agree? Okay. So there we have our closed form summation notation. There's a sub k. Ratio test says take the limit of the absolute value of the consecutive terms. There's our ratio test form. Okay, let's see. So we get limit a sub k plus 1 is going to be k plus 1 to the 5th divided by 6 to the k plus 1. We don't need absolute value bars. Everything's positive here. All right, so that's a sub k plus 1. If we divide by a sub k, that means flip a sub k. So that will be 6 to the k over k to the 5th. If we do a little bit of simplification here, we're going to have limit of, looks like 1 extra 6 in the denominator. So 1/6 multiplied by k plus 1 to the 5th divided by, oh, let's put that power on the far outside. So it looks like that. Okay, so that 1/6, let's put that out in front here. And what is that limit there then? That just does not look like a 6. Let's get rid of you, rewrite you. What's the limit of k plus 1 over k to the 5?
1.
I hear a 1. Going once, going twice. Anyone disagree?
As you expand, then you get k to the 5th over k to the 5th, and take the coefficients, divide, and you have 1.
So several ways you can think of it. One is that raising something to the 5th power, that's a continuous function, so the limit can actually come inside that 5th power. And the limit of k plus 1 over k, you know, you can say the divide by the highest power k, you could say, oh, let's just look at the quotient of leading coefficients, all those things you can say. This is not an indeterminate form. 1 to the 5th power is not indeterminate. 1 to the infinity is indeterminate. So that is our limit right there, 1/6. Okay, now for ratio test, what's our conclusion once we have our limit? Therefore, all right, therefore converge because that ratio is less than 1. So ratio test, root test, geometric series, under 1 converge. Under 1 converge. Speaking of roots, let's do the root test. So root test, we're going to take the limit of the kth root as k goes to infinity. So the kth root of all of this.
What's k through the absolute value, right?
It's the kth root of the absolute value, yes. And because there's no, let's put it in just to be safe, but we don't need it because everything is positive here. But let's put it in just to emphasize that it is absolute value. It's kth root of the absolute value. And again, it's all positive, so we don't really need it. So that means we can distribute that exponent down. And exponents, when we distribute them, they multiply. So the k through that, that's all going to end up being just 4k. Okay, so now here's one where it's not a problem all by itself to use the log limit thing. So we can use the shortcut here. So we can use the shortcut. So first thing we're going to do is flip. And if we flip, then we change the sign on the exponent. And then we distribute to put it in that standard form, that standard E form. And we look at these two coefficients there. And this will be e to the negative 20. So what's our conclusion with the root test? Less than 1, therefore converges. Exactly.
Converges absolutely.
Yeah, you don't have to say that when it's numbers that are all positive. If the numbers are all positive, absolutely convergent and convergent are the same. It's only if we have minuses sprinkled in that we need to say absolute. All right, should we take a break? All right, let's take a 10-minute break. and then we'll do a little bit more. Wow.
Crazy.
Shot. Okay, let's go to the comparison test. A marathon a day. That is just, that's pretty impressive. That is very impressive. Ooh, so he's probably done the Colorado Trail already?
No, I think that was his first time.
Oh, first time, and he did it the whole Continental Divide Trail. Oh, wow, that's nuts. Okay, let's go with the comparison test here. So with the comparison test, we usually are trying to pick our own B sub k. So B sub k is what we are choosing, and we're going to use that to analyze the A sub k. And so generally with B sub k, we're trying to get rid of the less significant parts. And when we look in the denominator, we have a function 5k and we have a function 4 through to k. 4 through to k is a bird wing, right? It's like a square root function. So it grows to infinity, but it goes very slowly. Y equals k or y equals x goes to infinity faster. So this is going to be less significant. So our first choice would be to do 1 over k or maybe 1 over 5k. We saw a couple of times that leaving that coefficient might be helpful in terms of getting the inequality to work the way we want it to work. Maybe we don't need the 5. Let's leave it in just to make sure. So our conclusion with this, if we look at the summation of B sub k, this is going to, if you wanted to analyze it, you could pull out the 1/5. And we know that multiplying a series by a constant doesn't change its convergence or divergence. And so this is going to diverge. You can say it a couple of ways. Usually we just say diverge because it's the harmonic. But you could say it's a P series and P is not greater than 1, so therefore it diverges. So it's a divergent harmonic. So if this dominant part diverges, then we suspect the whole A sub k series diverges. So we want to show then that A sub k is greater than or less than B sub k? Greater than, right, exactly. Ooh, good. You know, greater than diverging will diverge. You guys good. So we don't know. So put a little question mark. We got that. Then we do our cross multiplication. Subtract off the 5k's. And we can keep going as far as we want, but right here, this right-hand side is negative. So it's totally fine to stop there. As soon as it's really obvious, this is going to be true. So if that's true, what does that mean then?
That our A sub k diverges?
Yeah. So therefore, we have the original series is going to diverge by comparison test. Yes. Mm-hmm. So if we get a true statement there, then both series diverge. So this tells us that both are going to diverge. So if that's true, both series are doing the same exact thing. Both are diverging. All right, let's get down to the AST, alternating series test. So the alternating series test, that one is one of the easier tests to implement because the first part is the divergence test. So we just take the limit of A sub k. And now remember that with an alternating series, A sub k does not include the minus. So for an alternating series, notationally it's just simpler to refer to A sub k as that positive part. So step one for the AST, we want to take the limit of a sub k, as k goes to infinity. We're going to take the limit of this, and that limit is 0, so step one checks. And then step two is to show that the sequence of terms is decreasing. So we want to show that as we go further out, the terms are getting smaller. So we want to show that a sub k plus 1 is smaller than a sub k. So as we go further out in the series, we're getting smaller terms. So a sub k is 1 over k to the 3/2. Don't know, is it true or not? This is going to be a k plus 1 to the 3/2. Then we do our cross multiplication. So now we have matching powers, so we can unpower them. Take the 2/3, raise both sides to the 2/3 power. Or we can just equate the bases. If the exponents match, then the bases must match. And sure enough, this is true. So this is true. So second thing checks. So now we've shown both pieces of the alternating series. So therefore, we have regular convergence. So we know our alternating series converges. But anytime we have a convergent alternating series, we have this extra piece that we can go with. Good grief. That or that. So if we know it converges, then we can ask the deeper question, are the minuses necessary for the convergence? If you turn everything positive, do you still get convergence? So let's move this one out of the way a little bit. So now we're going to consider the series of positive terms. So we're going to consider this series where everything is positive. We take away the switch. So that's the series of absolute values. Series of absolutes. And does that series converge or diverge? Because?
P series.
P series, P is bigger than 1, yes. So make sure you write P equals whatever it's equal to, so I know you know. And then compare it to 1, and then make your conclusion. So P bigger than 1, that tells us that P series converges. So what is our overall convergence then?
Absolute.
So big, therefore, we have absolute convergence. Because the series converged and its absolute values also converged. So
Do we have one with the limit comparison test? Because we did the direct comparison.
we did do a direct. Yeah, we did not do a limit yet. Yeah, we'll try to find one. Okay, how about this series here? So same basic premise. We want to take the limit of a sub k. That's 0, that checks. So step one, just take the limit of a sub k. A sub k for an alternating, don't include the minus. Next, we want to show that the series is decreasing. So we want to show that as we go further out in the series, we get smaller terms. In your mind, you should see that it's true already, right? Because that fraction, as the denominator gets bigger, the fraction values get smaller. So it should be intuitive that it's going to be true. But we have to do the math. We have to show that it's true. If you want full credit, at least. So we've got that. First step is the cross multiplication step. And sure enough, we come down to a true statement. So if we get both those conditions to check off, so that and this is true, those check, that means the series of positives and negatives, the alternating series converges. That's going to converge to something. Now we want to classify that convergence. So now we consider the series of absolute values. So we're going to take the absolute values, and once again, we have a p-series. So we identify p, we compare it to 1, and that diverges. So what do these two things then lead us to? What type of overall convergence?
Conditional.
So this will be conditional convergence. Because the series of absolute values diverged. If the series of absolute values diverges, then you need the minuses. Got to have the minuses. Good. Good, good, good. Let's go with an IOC. IOC. So now we're dealing with power series. As soon as we see the x, we now know that we're dealing with a function. So these are power series. That means that there can be a whole bunch of different things happening for different x's. Some x's you plug in there, we can get convergence. Some you can get divergence. The one thing we know for sure is that every power series converges at its center. And what is the center of these power series?
0.
Yeah, they're both 0. Because you would see an x minus 5 or an x plus 3, you would see something other than just x. Okay, so we can use the root test or the ratio test for intervals of convergence. This one, it makes the most sense to use the root test because we've got this power on the outside. This one, we see a factorial, so we're going to go ratio. So let's go with the root test here. So we're going to take the limit as k goes to infinity, the kth root of a sub k. And here, we definitely need the absolute values because there's an x. X can be negative 5 million if you want. So then we get limit k3 to the k. So it looks like we're going to end up with 8k. Right, those k's cancel. We still have the absolute value. But the absolute doesn't need to go around 8 times k because that's always positive. K is a positive number. So that's our simplified expression inside the limit, the limand. The limand. The limand is dependent on k. So the only thing that has a k in it is the k. So we have that. The constant can factor out. The x does not depend on k, so the x can factor out. And what is this limit equal to? Infinity. So now with the root and the ratio test, convergence happens when the limit is less than 1. Is this ever less than 1? This is never less than 1. Therefore, the radius of convergence is 0. Therefore, the interval of convergence is not really an interval. It just contains the center of the series. Okay, so never less than 1. Therefore, it doesn't converge anywhere but the center. Let's go with the second one here. Okay, so here we're going to use ratio test. So we're going to take the limit as k goes to infinity. Ratio test, same idea. We need to take absolute values. So we're going to take the absolute value of the ratio of coefficients. Excuse me, the ratio of terms. Ratio of terms. So let's go with it. So this is going to be limit a sub k plus 1. And this is all going to be an absolute value. So this is going to be 2x to the k plus 1 divided by k plus 1 factorial. Don't need absolute value bars on that. That's positive. So there's a sub k plus 1. We're going to divide by a sub k. So that means multiply by the reciprocal. We've got that. And then we just have to simplify and then take the limit. All right, well, the 2's cancel, correct? All right, those are going to just cancel each other out. And then we're going to be left with 1x in the numerator. That 1x stays in the absolute value. It doesn't depend on k, so that can be factored out to the front. And then k plus 1 factorial, that can be rewritten as k plus 1 times k factorial. And so then those k factorials can cancel. So all that we have left on the inside is 1 over k plus 1, which is going to be 0. So when is this less than 1? So this is less than 1 always. So that means, therefore, the radius of convergence is infinite. So therefore, the interval of convergence is the whole entire real line. So everywhere convergent.
So if the radius is 0 or infinite, we don't need to check everything. But if it's finite.
So let's do that. So that's the next case. So these are the easiest cases, but it's very easy to make the wrong conclusion. So just make sure that you're clearly understanding that if this limit, you're always comparing to 1. This is never less than 1, so you have a tiny radius of convergence. This is always less than 1, so you have a huge radius of convergence. So let's do the middle of the road ones now. Okay, so here is one that will not be one of those extreme ones. It doesn't make sense to use the root test here because there's not a big root on a big power on the outside. So we're going to go ratio test. Ratio test is always kind of the natural way to go most of the time. So limit as k goes to infinity, the ratio of consecutive terms in absolute value. Okay, so this is going to be the limit of a sub k plus 1. So wherever there's a k, we're replacing it with k plus 1. So up here, this is going to be x to the 2k plus 3. Everybody see that? If you replace this k with k plus 1 right in here, you get 2k plus 2 plus 1, so that's 2k plus 3. So we're replacing the k's with k plus 1. And then down here, k plus 1 minus 1 is k. So that will be 5 to the k. Now we're going to flip a sub k. So we're going to have 5 to the k minus 1 over x to the 2k plus 1. And the x's have to have an absolute value. How many 5s and where? 1 5 in the denominator. We can factor it out to the front, in fact, since it's a constant. All right, now we've got to deal with the x's. So exponential base x, we subtract the denominator from the numerator, so 2k plus 3 minus 2k minus 1. So this is going to be x to the x squared. Yep, that has no k in it. We can even just cut to the chase here. Do we see any k's left whatsoever? No k. So the limit of a constant is itself. And we don't need the absolute values because x is squared. So that is the limit. There is no k. The limit of a constant is itself. Now once again, root and ratio test, we want to know, well, when is this less than 1? That's the big question. When is it less than 1? So that's what we need to know. When is it less than 1? Some x's are going to give us less than 1 and some aren't. So we just have to figure that out. So we're going to multiply both sides by 5. X squared less than 5. That means if you take the square root of both sides, which the absolute value of x is the square root of x squared. So this tells us that we have that interval that we're working with, negative root 5 to root 5. Okay, as soon as we have the x isolated, this, we can figure out our radius of convergence right there. As soon as we have the x isolated on the left, the whatever's on the right is going to be the radius of convergence. You can look down here. The interval is going to go from minus root 5 to root 5. Half of that is root 5. So there's our radius. But now we don't know what happens at these endpoints. So these endpoints, we are not sure. We can't write our interval of convergence down yet. We know the two goalposts. We know that we're going to go between minus root 5 and root 5. But we don't know whether we include or exclude. So now we get to do a little more math. We get to apply our chapter 10 skills. More math in math class. Shocker, right? So we're going to test x equals negative square root of 5. We want to know, does it converge at negative root 5? So we plug that in for this x. So we're going to plug that in for x right up there. So negative square root 5 2k plus 1 over 5 k minus 1. Okay, so tell me this. When we look at the minus sign here, the minus is getting raised to that power. Is that a switch or is that a constant?
That's a switch.
No. It's a constant. What constant? No. Yes.
Oh, yeah.
Do you see it?
It's not.
It's an odd power. Right? So 2 times k is always even. We add 1 to an even, we get an odd. So this power is always odd. And an odd power on negative 1 is always negative 1. So it's a constant. So it's not really a switch. So its value is going to be negative 1. So we can actually factor that negative all the way out to the front if we want. We don't need it inside anymore. So negative. And now on the inside, let's focus on this part now. The square root of 5 to this. Well, 5 square rooted is 5 to the half. So that half is now in the exponent position. So we have 5 to the half to the 2k plus 1. So that creates an exponent. If we put the half up there with the exponent, it's going to be 2k plus 1 over 2. Over 5 to the k minus 1. Got that. So let's rewrite this a smidge. Let's write this numerator's exponent as 5 to the k plus 1/2. Got that. And let's simplify this by combining those two powers. This is going to be 5 raised to the, we've got exponentials with the same base, so we subtract the exponents. So we're going to do the upper exponent minus the lower exponent.
5 to the negative 1/2.
5 to the negative 1/2. Good. Yep. No.
That does not.
No, not quite. Not quite. If we subtract this, it's going to be k plus 1/2 minus k plus 1.
Oh.
So the k's will cancel, but that's going to be a 3/2, right?
Yeah.
3/2. Okay.
And now it's going to
And so diverges by what test? The divergence test. Because the limit of a sub k, so let's just go crazy here and say, oh, well, that's a constant, it can factor out. So if it's a constant and it factors out, then we're left with this. So the constant can factor out, and then we're adding 1 to itself forever. Right? Summation of 1, 1 plus 1 plus 1 plus 1 plus 1. So this right here, the limit of a sub k is not equal to 0, therefore diverge. All right, so that means we exclude negative root 5, so our interval is going to have a parenthesis on the left.
Technically speaking, though, if you just removed the minus sign right there, and then you had 5 to the 3/2, that still wouldn't be 0. So then would you have divergence? Sorry,
Yes,
would you have
100%. Yeah, I know what you're
closed
saying.
interval on the right too?
Yeah, so exactly. So Austin is just pointing out that the only change is that when we plug in, the only difference is this minus sign. So we're going to end up with the exact same thing. We're going to end up with the summation of 1 with a coefficient out in front of 5 to the 3/2. And same thing here. Limit, ooh, that's not how you spell limit. Limit a sub k, again, will not be equal to 0, so therefore diverge. So our interval of convergence then is going to be open on the left and open on the right. A lot of steps. A lot more steps when you have a variable, when you have an interval of convergence that's bounded. All right, let's see what our composition. So composition is how we can build one power series from another. One power series from another. What are we going to replace the x with in our geometric series? So this is one of your known power series. You should know that one for the exam.
6x.
You're going to just replace the x with 6x. So f of 6x, the power series that we're looking for, so 1 over 1 minus 6x, all we have to do is come into this geometric series and replace that x with 6x. So we have 6x to the k. K starts at 0. And if you want to, you could come in here and separate this to 6 to the k times x to the k. Don't have to, but you could. Okay, now the interval of convergence. The original interval of convergence is -1 to 1, so that's x. If we replace x with 6x here, then we have to replace x with 6x there. So this is going to shrink our interval of convergence to that. So our interval will be negative 1/6 to 1/6. Do not have to test endpoints. We love composition because we don't have to check endpoints. Hate checking endpoints. So that is composition. Any concerns, questions?
Why don't we have to check endpoints?
The theorem just says that we don't. So when you do composition, like if we did check, if you did 5 of them and tested the endpoints, then you would realize, oh, the endpoints never change. With composition, as long as if with composition, if x is between these two numbers, then 6x is between those two numbers, and that's back to the original interval of convergence. So we haven't done anything that could possibly change the endpoints. So we're basically just shrinking or expanding the interval, but we're not fiddling with the endpoints. All right, let's take a look at multiplying by powers of x. So here we're starting with a power series for natural log of 1 minus x. So we've got this natural log of 1 minus x. We already know the power series for that. Now we want the power series for p. Well, p is just a multiplication by a power of x. So p of x is going to be this exact power series here, except all we do is multiply by x to the 7.
Did you put a negative for reason? Or what? Oh,
That's given.
okay, yeah.
It threw me off on the homework too.
So we've got that. So we multiply by this x to the, this 3x to the, stay. Really? So we're multiplying by 3x to the 7. So that's what's happening there. When we multiply by x to the 7, we're adding 7 to the exponent on x, and the 3 can just stay out in front. And so this, the interval of convergence, does not change at all. If you multiply by a power of x, your interval doesn't change at all. The idea is that if you were to form the ratio a sub k plus 1 over a sub k, if you multiplied a sub k by 3x to the 7, you're also multiplying a sub k plus 1 by 3x to the 7, so they just cancel each other out. So they're not going to change the interval of convergence. Multiplying by a power of x will not change it. Multiplying by a constant will not change it. So we like that. No endpoints to test. It's got to get worse, right? Ah, derivatives. It's not worse.
What about limit comparison?
We'll get to that
Thank
if we
you.
have time. We'll get to it if we have time. All right, so this is the hardest question
On the test.
on the test.
Not,
always
even,
the
not
hardest
even
one.
the integral test?
This is harder than the integral test. Because you have to figure out how to get to g from f, and that's not always obvious. I think it's harder. Okay, so how do we get to g from f? Derivatives or integrals? Let's try. So f prime,
Oh, to g from f?
to get to g from f.
We integrate.
Yeah, because this we know the power series for. That's just a modified geometric. Okay, that's a modified geometric. This one we know. So we want to get to g from f. So if we take the derivative here, we can, if we want, we could rewrite, there's a couple of ways you could do it. You could use the quotient rule. You could write it like that. So then we get negative bing to the -2, bring down the power, subtract 1. Now multiply by the derivative of what's in here, so that's going to be 10x. So if we simplify this, let's see if that helps us. That's 10 at negative 10x over 1 plus 5x squared squared. So there's f prime of x. So did we do the right thing?
Well, it's the same except for the -10.
So how do we get to g from f then?
It's f prime of x divided by -10.
Yep. Right? Everyone agree? If we take f prime of x and then we divide by -10, we're going to get an exact match. All right, so that tells us then to get the power series for g, get the power series for f, take its derivative, divide by -10. So let's get the power series for f. So f is going to be based on the geometric series. So the geometric series is one of our root power series. That is the sum of what?
X to the k.
Just x to the k. And the interval of convergence for this power series, -1 to 1, excluding endpoints. So that's where we're starting. That's the geometric series. Now, we want that, so we have to do a little bit of modification here. The first thing that we can do is replace, it's a little easier if we replace x with -x right away and just make this positive. So if we replace x with -x, we have this. And that's not going to change the interval of convergence. So there we replaced x with -x. So here the x's became -x. All right. Now what are we going to replace x with? 5x squared. So now x is going to turn into a 5x squared. So anytime we see an x, we're going to replace it with 5x squared. So on this side, 5x squared all to the k. And then also in this interval, we have to do that. So for our interval, let's focus on that for a minute. This is going to be -1/5 less than x squared less than 1/5. And then our little sneaky algebra technique was to do that. And then we can take the square root of both sides. The square root of x squared is absolute x. That's 1/√5. So this tells us that this interval of convergence goes from -1/√5 to 1/√5, but we don't know about the endpoints yet. So we just know the left and right endpoint, but we don't know whether we include or exclude. All right. So we now have the power series for f. We just have to figure out, oh, I made one comment right there that was not true. Do we know these endpoints? We actually do know those endpoints because we haven't taken a derivative yet. It's once we take a derivative that we have to change endpoints. If we do a substitution, aka composition, then we just talked about this a minute ago. If we just do a composition, we don't need to change or test the endpoints. So if you do a composition, you just put whatever you're composing in for the x, and then whatever you get, you get. So that's what we like about composition. We don't have to test the endpoints. I jumped the gun, because we're going to have to test the endpoints soon. All right, so now we have f right there. There's f. So f prime of x, power series for f prime, we take the power series for f and take its derivative. All right. So we're going to take the derivative of this power series. When you take a derivative, let's see, that's a constant, -1 to the k, that just floats down, there's no x. There's just a coefficient. Now we have to differentiate this. And maybe it's going to be easier to rewrite this as 5 to the k x to the 2k. All right, so the 5 to the k is a constant, so that when you take the derivative of a constant, it just comes down when there's an x, at the end of it. So the constant's floating down, and now we have to differentiate the variable part. The derivative of that is going to be 2k times x to the 2k minus 1. This series is going to start, maybe not at 0, because when you take derivatives, you usually lose a term. So let's check. So the very first term here, if you plug in k equals 0, that's going to be a constant. The derivative of that's going to be 0. When k is 1, you're going to be differentiating 5x squared, and that derivative is 10x. So our first non-zero term over here should be a 10x. Let's check. And when we plugged in a 1, this would be negative, so it should be a negative 10x. So we come over here. Obviously, 0 doesn't work, because we get a negative exponent on x. That's not a polynomial. It can't be part of a power series. Power series are powers of x, positive powers. So if we plug in a 1, let's see where we end up with. Plug in a 1. 1 times all this stuff is going to give us negative 10. Plug in a 1 up there, negative, we're going to get a 1 for the exponent on x. We're going to get the negative 10x that we wanted. So we want to start at 1. So we lost one term, very common. So there is the power series for f prime. Now the power series for g, we said to get to g, we're going to take the power series for f prime and divide by negative 10.
So multiply the entire sigma notation by -1 over 10.
100%. And this starts at 1. And we could do some simplification. We'll do it in 1 second. Okay. So the only thing on the inside that can come out is the 2. So we're going to get -1/5. So now we have our power series. All right, so there is G written as power series. Okay. Now we need its interval of convergence, so we have to test those two nasty-looking endpoints.
Wait, don't when we have derivatives we lose conversions?
No, that's generally what happens, but we have to test it still, because we don't know for sure. Usually that's our pattern. It depends on the type of function. Most of the functions we deal with, yes. So now we have to test the endpoints. Yeah, this one's kind of gnarly for sure. The one on the exam will be a little less gnarly. So we're going to test x equals -1 over the square root of 5. So that's going in for the x. So we don't care about this -1/5 in front. A constant does not change convergence or divergence, so we don't really care about that. So let's focus on the inside. It's definitely an alternating series. 5 to the k times k. And now, that thing, that's going to be plugged in for this x here. So we're going to have negative 1 over the square root of 5. 2k minus 1. So we're going to have something kind of similar to the other one we looked at. So we have this 5. The 5 we would like to combine with this 5 down here. So let's just clean it up a little bit, and then we'll see that the limit of a sub k is what it is. So we're going to get a negative 1 to the 2k minus 1 divided by 5 to the, let's do what we did before. That's 5 to the half. So if we multiply this by a half, we're going to get k minus 1/2.
Shouldn't we have the 1 beneath the summation sign as well?
And this is going to start at 1, yes. Okay, so let's combine, and then hopefully we can see what our limit's going to be. So we have our summation. So what is the new power on negative 1? 3k minus 1. 3 times k is 3k minus 1. Isn't that just still a regular kind of switch? Because 3k minus 1, if you plug in a 1, so if you plug in an odd, so like a 1, you're going to get an even. 3 times 1 is 3 minus 1 is even. If you plug in a 2 into 3k minus 1, you're going to get an, so let's plug in 1 and 2 and just notice. If we plug in a 1, we get an even, and if we plug in that, we get an odd. So it's going to just alternate odd even. So this is still just a regular switch.
So
Okay.
could we just write it as negative 1 to the k since they both function the same?
As long as they match properly.
I mean,
So-
but in this case, since they match properly.
They aren't going to match. Are they going to match properly? So if you plug in k equals 1 here, you have a negative. If you plug in k equals 1 here, you have. So you'd have to just. You could modify. You could just make it k plus 1.
Yeah, just to make it.
Less
Pretty.
weird. Yeah, absolutely. So now we've got the 5s. The 5s are going to be the hardest part here. So 5. What's the power on the 5 going to be?
Negative 1/2.
Not quite. So it's this power of k minus the denominator's power on 5.
So 5 to the half.
5 to the half. So square root of 5. That can come out to the front. That's a constant. Everyone agree? All right, that 5 to the k, 5 to the k, that's all going to simplify to a constant. So the only thing that's left here now is k. That's all that's left. So that all switched into a square root of 5 on the outside. The negatives combined to that switch. What's the limit of a sub k? Infinity. This is a sub k. For an alternating series, you do not use the switch. So here the limit of a sub k is not equal to 0, therefore diverge. And then like we saw with the last one, there's only going to be a minor variation when we go to the other endpoint. So when we test the other endpoint, when we go to the other endpoint, let's look. Right here, this is the only part that's going to be different, right? It's just going to be this switch part. So instead of getting this modified switch, we're going to have the original switch. So nothing's going to change. We're going to get the square root of 5 out in front. We're going to get negative 1 to the k. And we're going to have a k here. So we're same basic idea. And so the same basic idea, we have the same result. The limit of a sub k is not 0, therefore it diverges. Therefore, our interval of convergence includes those, doesn't include those endpoints. So this is going to be our interval of convergence. So therefore, I will equal -1 over root 5, comma, 1 over root 5. So that's going to be the interval of convergence for the new function g.
So how do you know that taking the derivative or dividing by 10 doesn't change the interval?
Because of the ratio test. So the ratio test does a sub k plus 1 over a sub k. If you multiply a sub k by 10, then you're also multiplying a sub k plus 1 by 10. And when you form that ratio, the 10s cancel. So that's why multiplying by a constant or a power of x doesn't change the interval. Because you're using the ratio test, you're essentially multiplying a sub k and a sub k plus 1 by the same thing. Then those things just cancel in the ratio.
And the derivative?
Say that again.
And with the derivative?
And with the derivative, that's why we have to retest the endpoints on the derivative, because the derivative could change stuff at the endpoints.
But it doesn't change the interval.
Not in this case. Oh, it doesn't change the endpoints. Like the endpoints are going to be where the endpoints are. The only thing that can change is whether we include or exclude. Yeah. The endpoints won't change though. The endpoints will stay the same. All right, let's go to a binomial.
Wait, when you say the endpoints, you mean whether it's included or non-included, or are you talking about the interval?
When you do a multiplication by a constant or a multiplication by a power of x, the interval doesn't change at all, including whether you include or exclude the endpoints. So the endpoints are the endpoints, and then the question is, do you include or exclude? So if you multiply by a power of x or a constant, you don't change anything. The interval stays the same. The interval.
So taking a derivative or integrating.
Taking a derivative or integrating, the endpoints stay the same, but you might include or exclude them differently from the original. So that's why we test the endpoints. All right, let's get to a binomial. So binomial expansion for 1 plus x to the half. So remember that this part is always going to be given to you. You can't figure out the interval of convergence for a binomial. So that's always going to be given to you. So we look at this. This is just substitution. So it's substitution. This is one of our favorites because we start with the expansion for that, and then we just substitute. We substitute into the interval. We don't have to test any endpoints. So we love that. Okay, so first let's build our power series for this. So this is going to be 1/2 is the power, choose 0. It's going to look a lot like a geometric series. So then we have 1/2 choose 1 times x. So here is what our expansion is going to look like. 1/2 choose 2 times x squared plus 1/2 choose 3 times x cubed, etc. So that is the binomial series expansion for root 1 plus x. 1/2 choose 0 is 1. 1/2 choose 1 is 1/2. So those two are always going to be autopilot. And then for these, 1/2 choose 2, we start with the 1/2, we subtract 1, and we keep subtracting 1 repeatedly until we get k factors. K is the lower number. So with this one, it's really fast. Choose 2 means just 2 factors. So this will be -1/8. So that is what goes right here. -1/8 x squared. And then we have one more coefficient. We want to get to 4 non-zero terms. So 1/2 choose 3. We start at 1/2. We do repeated subtraction until we have 3 factors. And then divide by 3 factorial. So this will end up being, let's see, we have 3 in the numerator, divided by 8, and then we multiply by 6, so 8 times 6 is 48, and then we divide by 3, so we get 1/16. So plus 1/16 x cubed plus etc. So there is our binomial expansion for 1 plus x to the half. Now we want to replace x with negative 4x. So we just come right through here, and anywhere that we see an x, all these x's get replaced with negative 4x. So negative 4x here, so that's going to be negative 2x. Negative 4x here, let's see, the square is going to wipe out the negative from the negative 4x, so it's going to be 16x squared. So it's going to be 2x squared. And then here we plug in negative 4x. That negative is going to preserve because we have an odd power. So we're going to have an x cubed. And the coefficient, 4 to the 3rd power. Let's see, we have 4 squared in the denominator. We're going to have 4 cubed in the numerator, so that's just going to leave us with a 4. So there is the power series for 1 minus 4x to the half. And now we have to go to the interval of convergence. So we have negative 1 less than or equal to. Instead of x, we have negative 4x. So again, the nice thing here is we're not going to have to test endpoints. We just have to simplify the radius of the interval of convergence. So we divide by negative 4. When you divide by a negative, you switch the inequalities. And so this tells us that our interval of convergence, negative 1/4 to 1/4, including the endpoints. So substitution, composition, that's the simplest thing. If you're just substituting, we don't have to test endpoints. All right, any piece of that? All right, let's go to a definite integral. And
Will you fill in the rest of this over the next couple days?
yeah, I can fill in the rest of it, yes. Yeah, that's good. I'll fill it in. I can do it tomorrow.
Okay.
I gotta go deal with my car tonight. So, same type of expansion. We just did this type, right? So we do that. You do this the same way we just did it if you had to find this on your own. So we've got it right there, and then this will be 0 to 0.3. And all we're going to do is replace all the x's with x to the 4th. Okay? So we're going to have 1 minus 1/2 x to the 4th plus 3/8. X to the 4th into there squared, that's x to the 8th. And then here, minus 5/16, x to the 4th there, multiply, we get 12, plus etc. dx. Then we integrate term by term, it's polynomial. we're going to add 1 to each of these exponents and divide by the new exponent. X to the 9, dividing by 9, a 3 will cancel, so we'll end up with 1/24 in front here. This will be x to the 13. 5 over 16 times 13, which we already did earlier today. So we get that. And this will go from 0 to not to 0.3. The 0 is going to contribute nothing. So the alternating series that we're going to look at is 0.3 minus 1/10 times 0.3 to the 5 plus a 24th times 0.3 to the 9 minus 5 over whatever that number is. Was it 1020?
208.
Oh, it's just 208?
16 times 13.
208?
Yep.
Oh, that seems so small all of a sudden.
What is last?
Is it the same as it was last time?
Fortunately, numbers haven't changed.
Fortunately, multiplication is constant. All right, so now we just have to figure out what term is under, was it 10 to the negative 3?
Yes.
10 to the negative 3. So we'll do that by looking at our calculator. All right, I'm going to just go with the 0.3. I'm going to go 0.3 to the 5. 0.3 to the 5 divided by 10. And that one's already smaller. Right, we did 10 to the negative 3.
Yes.
Right, so that's already smaller. So, oh my gosh, 0.3 is not smaller than it. Okay. So, oh, there's 2 pens here.
The approximation.
So the approximation is 0.3, exactly right. So this term right here is less than 10 to the negative 3. Therefore, we're going to add these in front, nothing to add. So therefore, the integral, I don't want to use an I. Let's use a gamma. Not a gamma, an omega. So that's going to be approximately 0.3.
Yeah.
Yeah. Approximately 0.3. Interesting. All right, any questions? Good. All right, so I will fill in the blanks that we didn't get to. I'll fill those in. I won't be able to do it till tomorrow, but I'll do it tomorrow. Tonight I've got to go deal with a car. But I'll do it tomorrow when I get to school.
What happened to the car?
I had to get brakes and tires and things. Cars, maintenance, winter. Winter's coming. I'm putting my snow tires on, getting new brakes.
Then you said we don't have to worry
Because my
about-
car shakes like this when I hit the brakes. So it seems like a bad thing. Yeah, all that stuff's going to happen.
Oh, that's what
Everything's happening.
And then you said the application.
Well,
question-
no, I dropped it off this morning at 8.
So you have your time.
Yeah. Yes, yes, yes.
and then-
All right, good luck studying.
Yeah, this question,